So welcome everyone, welcome back for the last session, and as usual, the last is the most exciting one. So we have two quantum presentations. I believe that at the moment, Christopher Monroe already can see me. Is that a fact or not? Yes. So it's my pleasure to introduce you to Christopher Monroe. Here it is. Unfortunately, well, people sometimes get sick. And I want to acknowledge that he still makes an effort to join us via video call. So we keep with the program and we keep the balance to the call to, look, here I am. Look, Mom. So, as I always say, everything that you need to know about Christopher Monroe is on the personal page. I strongly encourage you to look at it. It's spectacular. So really sorry that he cannot be here to interact with us. Having said that, we will be able to. I haven't done anything yet. So I was saying that there will be live Q&A, so he will be able to interact with you, right? So vice versa, he will be able to ask questions to the next speaker about quantum computing as well, so it should be fun. Standard question to technical guys, are we okay? So I can leave here and then we welcome Chris Monroe.
Okay, thank you, Nicholas. Everybody can hear me all right? Okay. Again, I greatly apologize for not being there myself. It was 4 flights and a 48-hour ordeal, and I figured that would probably kill me. And I know it's hard to pay attention to. I don't like video presentations either, so I'll try to be controversial with some zingers in there to make up for it. And I know you can't throw tomatoes at me, so all right. So the subject is quantum computing, of course, and I'll speak for a little while, and then Russ Stutz from Quantenium will pick it up. And so my talk will maybe be a little more general, and I think Russ can tell us a little about the great things happening with the quantum computers at his company. Okay, so let me just dive right in with a perhaps hypey slide. Well, this is when you're starting a quantum business, you need to have your hockey stick curve if you want investors. Now, on the one hand, this is not hypey at all, because we know that the future of computing, for it to keep growing like it did for the last 50 years, there has to be something new. And quantum, we don't exactly know how it's going to play out, but eventually it's going to not take over everything, but it's going to do things that we can't do now, and probably other things when we find out its full breadth. And so I would say the single piece of hype you'll find in a plot like this is the timing. So when we transition from conventional or classical computers to quantum computers, some people say, well, it's already here, or it's in a few years. It's certainly not. Otherwise, they would be all over the place. The money would be, the floodgates would open to the funding of quantum computing companies. That hasn't happened yet because there's no useful commercial app yet. And our quantum computers are still not powerful enough to even beat my laptop. So, but the principles are there, and we're starting to build big things, a lot of progress, but we still have to wait a few years. So I think it will probably happen at some point. And if you have to peg me down, you can ask me later, I guess, but it's not next year. It's probably not 5 years. Okay, so why did I say that classical computing is sort of tapering off? Again, this is not exactly the right story to introduce quantum computing, but as we know, Moore's law is starting to hit physical barriers This is a version of Moore's law in the number of transistors scaled to 1978, and roughly a factor of 2 more every couple of years. And over the last 10 years, it's really tapered off, because when you get down to sub 10 nanometer scale, these transistors are now approaching the size of large molecules. And it's getting more expensive per bit to even engineer those things at a few nanometers like they're doing now. And eventually, when they get down to 1 nanometer, they're not going to be able to make them smaller, because you're going to see the granularity of those big molecules. I suppose you could always break apart the molecules, but then that's like having it's like having a nuclear reactor in every processor. We don't want that. So Moore's law won't continue. Of course, that doesn't mean architectures won't grow, and we'll be able to get, still huge growth by doing things more, doing things better on the architectural side. Clock speed hasn't really improved in a long time. I may return to that topic. But looking at this Moore's law, I want to go way back in time to Richard Feynman, American physicist, as you probably know. In 1959, I think he was moved by the silicon transistor, the first demonstration of a solid state transistor, displacing from vacuum tubes. And I think he, as one of the founding fathers of quantum physics, quantum electrodynamics, he was also a tinkerer, and he realized that you could, it was possible to shrink semiconductor circuits down to individual atoms and do computing. And so he has this zinger in a speech he gave, 1959. He said, when you shrink down to just a few atoms for your transistors, there should be new opportunity for design. And the reason is there's new laws of physics playing a role at that scale. And those laws are called quantum mechanics. And so what does that have to do with computing? It really hasn't played a direct role in computing. The transistor is quantum, but so am I. Everything's quantum. That doesn't really help you. There are classical laws that we can use to understand how transistors work in classical computing. But quantum mechanics is a radically different theory. And when applied to bits, we have these things now called qubits or quantum bits, you may have heard. And the radical feature of quantum bits is that they can be in a superposition of 0 and 1, not definite state 0 or 1. They can be 0 and 1 with arbitrary weights, 50-50, 90-10, and so forth. And the trick is, of course, those qubits are in a superposition only until you measure them, only until it interacts with the environment or you make a measurement. And then it sort of relaxes or collapses into one of the definite states. That's quantum mechanics, basically. There's a differential equation describing how that goes. We really understand all that stuff. So when applied to computing, it took probably 30 years after Feynman's speech here that it was recognized there could be something new here, basically a quantum parallelism. So let me tell you that story. I see it as a good news, bad news, good news story. So the first piece of good news is that when you put a few qubits together, you get exponentially many configurations. So with one qubit, there are 2 possibilities, 2 bits. But with 3 qubits, there are 8 3-bit numbers, so you can store a superposition of all 8. And this is a little bit of quantum jargon. We have our own math. This symbol with a line in the bracket means that's the quantum state. It's abstract, just like TTL logic. It can represent really anything that's a 2-level system. We have 3 of them, and we can store 8 numbers simultaneously. And these 8 parameters are continuous. They follow a wave equation, and you can push on the system to make the wave equation sort of interfere and split and so forth. And the parallelism here is sort of drawn in a very crude way here with this black box. If we have a function, we can compute a single time and get 8 answers in a way. We can say compute the logarithm of the input, but if we have a superposition of 8 inputs, we've computed 8 logarithms with 1 computation. Okay, that's the good news. And with 3 qubits, it's not so interesting, as 8 is still a pretty small number. But with lots of qubits, even 300 qubits, that's a very small chunk of matter. If a qubit is a single atom or a single electron, 300 of those is still a tiny, tiny speck of matter. But with just 300 qubits, 2 to the power 300 is the number of configurations you can, in principle, represent and control. Well, that's a huge number. That's 10 to the 90th. That's more than the number of atoms in the universe. So it's not hypey to say that with a small quantum computer, you can do things that will always be impossible with classical computers because there's frankly not enough space in the universe. Okay. So that's really good news, of course. And I think Feynman probably was immediately aware of this. But the bad news is, remember, I told you when you measure a qubit, it collapses to a random value. And what good is a computer if you can't look at the output? so if you compute these 8 numbers or 2 to the 300 numbers, when you measure an output, you're just going to get one of the outputs, and you have no idea which one. So it's a total noise-making machine, and it's no better off than a classical computer. So that's really bad news, of course. And as I said earlier, in the 80s or 90s, it was recognized that there's something you can do before measurement that is the final piece of good news. And it's very hard to draw here, but imagine these input states. They all interfere because they follow a wave equation. These red dots are actually called quantum gates, and they're analogous to classical gates, like a NAND gate, for instance. And they allow paths to interfere. They change these amplitudes, these weight factors of all the numbers. And there exist algorithms. Here's the statement, the final piece of good news. There exist algorithms that don't take so many of these gates that allow an interference, a massive interference to occur where only one or a few answers are possible at the end. And then when you measure them, it's not so noisy. It might not be just one, but imagine we had 2 to the 300 inputs and we had something like 300 outputs. That's not so bad. Just repeat the experiment several thousand times and you'll get all 300 outputs. You'll get that distribution. And those outputs can depend on all 2 to the 300 inputs. So there exist algorithms that can be cast in this form. And this is really what quantum computers are at kind of a high level. Okay. Now I'm being very vague here because there are very few known algorithms that can be cast in this form. And in the 90s, we learned of one of them that's probably the most definite quantum algorithm, and that is Shor's algorithm for factoring numbers. You've probably heard of it. It makes factoring algorithmically easy, or at least not exponentially hard. I guess that's mathematicians call that easy. And well, we don't know that factoring is a hard problem classically, but there is no known or at least public classical algorithm that can factor efficiently. And as you know, factoring, the difficulty of the factoring problem is what underlies almost all public key encryption systems, including RSA. So there are a lot of 3-letter agencies and nation states that are very interested in quantum, I guess, to break codes. Here in the US, we know that NSA is really interested in this, not just to break codes, but to know when our existing codes are going to be useless. That's very important for them to know that. So the complexity of Shor's algorithm takes the best known classical factoring algorithm, which is the number field sieve. And as you can see, this is exponential in the number of bits that represents the number you're factoring. Well, it's not exact. I guess this is called super polynomial, but it's worse than any polynomial. And Shor's algorithm makes it a straight polynomial, n squared log n, something like that. This is a big deal. It really changes the complexity of a very important problem. But for us in quantum, we can identify at least one use case. Now, the problem, of course, n squared log n is still not great. To factor a big number, you need n is, 2,000 bits. So n squared is 10 million bits. Maybe you're doing error correction. You might need 1 billion bits to really factor an interesting number. So factoring, although we know exactly how it works, we know exactly the pattern of gates we need to build here. It's just way too hard for today's quantum computers. 1 billion bits, maybe 1 billion bits, maybe 10 billion operations. And right now we have the state of the art is maybe 100 qubits, maybe a few thousand operations. So we're way far away from that. Well, the good news is we just sort of started building these machines. And let me skip this part here. We were just building these machines, and there are a lot of problems that can be cast in the form where you have lots of inputs and only one output. For instance, any optimization problem, and there are lots of hard ones. Most of them are like combinatorial optimization problems are really hard if they have a lot of if there are a lot of variables, and there's only one answer. There's only one optimum. There's only one tallest mountain peak in this landscape. This is just two variables. It's very easy to see the optimum. But if you have 10,000 variables, it's very hard to find the optimum value of some nonlinear function. And the traveling salesman is an example of that type of a problem. Any logistical problem like that, if we can map the cost function in this traveling salesman problem to a bunch of gates that play with the energy of a bunch of qubits, there might be a heuristic way to use a quantum optimizer. And this is not proven. In fact, we believe that a quantum computer cannot solve for the best case, but it might be able to solve better than any classical heuristic. Okay, so that's sort of conjecture, and we have to build it and just sort of see. Another area of optimization, this is not usually called an optimization, but modeling molecules, finding the ground state energy of even the caffeine molecule here only has 100 electrons. We can't solve it exactly. What's the conformation, the ground state of caffeine? And it's because the electrons optimize their free energy and their many body interactions. It's a physics and chemistry problem. So it's sort of naturally mapped onto qubits, maybe not qubits, but quantum systems that we can use to compute. So that's a very exciting field as well. Well, I'm an experimentalist. I build quantum computers, and I do believe that you cannot divorce the building of quantum computers from running them and finding applications. I think, unfortunately, too many people were steeped in these wonderful computers now where we don't think about transistors. I mean, how many of you think about, well, some of you probably do. How many of you on the software side think about transistors? You probably never do. You don't have to because they work so well. They're sort of commodities. In quantum computing, it's like being in 1940. We don't know how to wire them together for a particular application. They have lots of errors. So we really have to co-design. That's a word I stole from your community. Actually, my sister, Laura, in the crowd there, gave me that word many years ago. It's what we have to have in quantum computing, probably for the next several decades, before we have commoditized qubits. And then you can, like your iPhone, you don't have to care what's inside. You can just use high-level quantum software. Unfortunately, most of the companies out there now, the startups, are doing quantum software to nowhere because they're not married to a particular hardware, and you really have to do that. So what about the hardware? There's sort of, I've given you one of the major challenges in quantum computing. We don't have any apps. Well, we have factoring, but that's sort of off the table. We can't prove any apps. We don't know what they're good for yet. The second challenge is that we don't know how to build them. We do know how to build them. They're really hard and really expensive to build. And if you don't have an app that's commercially making money or promising, how are you going to pay for it? So those two challenges, they're intertwined. And I think you have to attack both at the same time. So this plot, don't read the fine print so much. I stole it from a Science magazine article almost 10 years ago, and it listed the popular candidates for building these devices. I split them into two camps. On the right here, we have what I'll call synthetic qubits. These are qubits made in solid state systems. They're fabricated like in silicon, or superconducting loops are very popular. These are the solid state systems, and they don't work. They really don't work well. Now, that's unfortunate because we have a VLSI community, we have Moore's Law, we have companies like Intel and IBM and all that. They really don't know what they're doing because they're still stuck in the solid state qubit landscape, and nobody knows how to scale them. And there was an announcement just today or yesterday about Microsoft's new topological Majorana qubit. It can't do anything. They have no idea. They really don't. And the big companies, I'll go ahead and be controversial here. It's not controversial. The big companies are sort of the worst at the hype because they're not paying for it. Their stock price is not based on their stance in quantum, so they can say whatever the hell they want. But I think we should also thank them for bringing a lot of attention to the field. That's very cool. I do think that startups are going to, like most new tech, startups are going to carry the day in quantum computing. And most of the startups are on the left here. This is a different type of hardware, what I might call natural qubits. Atoms, individual photons, individual electrons, individual atomic ions. That's what I'm going to talk about a little more, and Russ will follow up. These are standards. You don't fabricate an atom. The atom exists already. It's already fabricated. You do have to isolate it. You have to hold on to it and poke at it with laser beams. A lot of exotic stuff. But what we don't worry about is the qubit and the cleanliness of the fab. It's perfect. Atoms are the best timekeepers we have. They're called atomic clocks, and that's for a reason. Every atom of ytterbium isotope 171 is the same in the universe as far as we know. So you don't have to worry about replication. It's perfect. You do have to worry about the engineering, and unfortunately, all the engineers are over on this side, wasting their time with bad physics. We need those engineers to come on over here, and it is slowly starting to happen. So here's an example of some pretty amazing engineering. This chip here, it's about 1 centimeter across. This comes from Sandia National Labs. They're the America's government silicon fab. They make mostly radiation hardened processors, but they have an R&D team that actually makes ion traps. This is called an ion trap. Now there's about 100 electrodes. I won't get into the details on this. Russ might talk more about the Quantinuum and Honeywell traps. It's very similar technology, but this is all at room temperature. It's not even cold. But what's exotic here, these dots, these blue dots, these are individual atoms, one at a time. They're charged atoms. That's why they've repelled each other, and they're held in something called an ion trap. And they float above the surface here. The picture expands them, but they're about 1/10 of a millimeter above this surface. But that's really far. Atomically speaking, that's really far away. Because they repel each other, they form an equilibrium separation. They're about 5 microns apart or so, depending on the system. And each atom is an atomic clock. And each atom has an atomic clock with a frequency that ticks very regularly. This is our qubit, 2 levels that have an energy separation given by Planck's constant times this frequency. Okay, so now why do you see these atoms? They're glowing blue because we're shining laser light on them. And this particular laser light causes them to fluoresce. Remember, you don't want to measure qubits until you're done with the computation. So this is a measurement step where we're measuring every one of them. There's also something called laser cooling that happens. These atoms are brought to rest, even though there's no cryogenics here. They're brought to rest with something called laser cooling, invented 30 years ago, several Nobel Prizes around it, including both Russ's and my thesis advisors. They have Nobel Prizes on laser cooling. So the idea here in an ion trap quantum computer is that we're going to poke these atoms with lasers. They're floating in free space. Oh, I forgot to mention, this is our piece of exotica. These atoms are in a vacuum. There's no air. So it's sort of the limit of perfect isolation that you need for a quantum computer. This is the most perfectly isolated quantum system known to man, a bunch of individual atomic ions. Okay, now a physics slide, if you'll bear with me. It's actually pretty easy physics, believe it or not. How do we make a gate? How do we interfere the qubits in a collection like this? There are several ways to do it, but the basic way in trapped ions comes down to this. Let's say we want to make a gate. That is, we want to make a particular superposition that connects 2 of these qubits. What we do is we poke a laser beam at the 2 qubits in question. So these are a bunch of ions here. This is actually a real crystal, picture of a real crystal. Now these laser beams are focused very tightly so that we can address individual atoms. These are like our wires. We can't have real wires. Real wires are not quantum. Even if they're cold, they're horrible quantum systems. We don't want wires. But lasers have a nice soft touch. And the idea is this laser will apply a force. It's called optical tweezers. It's called a dipole force also. You may have heard those terms. But when we focus lasers and tune them in the right way, this force can push or pull the atom depending on its qubit. I've labeled the qubit as up or down. You can think of that as 1 or 0. Those are the 2 levels. And if both atoms are in up, they both move up. If both are down, down, they both move down. If they're in the odd states, up, down, or down, up, they move apart a little bit. And that's key, because if they move apart a little bit, their Coulomb repulsion, these are ions, their repulsion is a little different. And you can calculate an energy difference between all the configurations. I won't, there's some physics here, but the truth table of those two ions is that if they're in the odd parity states, they suffer a phase shift. That's basically the wave equation. When you change the energy level of a quantum system, you get a phase shift. And the two odd states feel this phase shift. Notice the phase shift is exactly the same. It's a complex phase here. And when you make that phase pi over 2, it's as powerful as a NAND gate. It allows you to do the universal gates you might need in Shor's algorithm that I mentioned. Okay, so that's it. There's a lot of physics here. It's mechanics is what's going on. We're pushing atoms around. Now, there's a lot more details on this for those of you that are know something about quantum gates. This is called an Ising gate. It's sort of the universal gate that we use in trapped ions. It's not a NAND gate. The gates are very slow, relatively speaking. They take maybe hundreds of microseconds to operate, which is slow for a computer. But this is a quantum computer, and like you see, a new computer can be slow as long as the complexity is good. You'll always be able to make up for the slow clock. So that this idea was pointed out a long time ago, Chirac and Zoller in 1995. I happened to be in an atomic clock lab at the time where we were doing this already to make better clocks. And we started just kind of changed direction and said, you know what? I think we're making quantum computers now. That's literally what happened when I worked at NIST in Boulder. So this is an example of a fully programmable, full stack quantum computer at a university, which is a little odd. We were funded at a very high level from the NSA and IARPA and so forth, and more recently by the DOE and NSF, the civilian agencies, who are very interested in quantum computing for science, and lots of collaborations with companies and so forth that allowed us to integrate everything that goes in. I'm not going to get into the details. There's a lot of optics, a lot of lasers, but this box is closed for many months at a time, and we program everything from outside. So we're able to really pay attention to the software. Now, I will say that the vacuum that I told you, the latest version is a really small vacuum chamber. My colleague Jung-Sang Kim here at Duke has really devoted his life to engineering things, making them smaller and better and so forth. So with a system like this, we're able to pay attention to the quantum computer stack in an academic setting, which is really fun because my work has all been down at the very bottom, underneath all these pancakes, smashed by everything else. But we have these atoms and laser beams. We control them with optical modulators and lasers, and then we want to compress the gates into circuits and algorithms. And a user might not care about any of that, but they want to run a routine. So we're working with. We're not just doing physics anymore. I like to say, certainly engineering, and we're branching out into computer science. And this is why I'm starting to learn a little bit. I'm a novice on computer architecture. Things that your field is very adept at. In the ion trapped version of these different stacks, there's a lot of optics, but there's a lot of translation between universal gates in a textbook and the ones that we have that are native to our hardware. And this is the aspect of co-design I said earlier, it's so important. You need to be able to translate that and perhaps make shortcuts so that your libraries and algorithms use the native gates of your hardware. Okay. I wish I had more time. There's tons of collaborations and fun experiments we've done throughout the years. I will talk about one pretty recently in a collaboration with Umesh Vazirani, Norm Yao, Thomas Vadik on certification that you have a quantum computer. How do you know you have a quantum computer? Well, you could run Shor's algorithm. That's great. What's wonderful about Shor's algorithm is that you can verify it fast. Because if I promise that I factored a number for you, you can just multiply them together. You don't need a quantum computer to verify. Now, other problems, you need a quantum computer to verify that you had a quantum computer. And the biggest example is everything that Google's doing right now. They're generating noise. They're generating a certain pattern of noise. And to prove that they have a quantum computer, they're basically saying, you can't model that noise with your classical computer. So that's very indirect. To prove you have a quantum computer, you're basically saying, well, you can't prove we don't. So that's really indirect. And also generating noise is not incredibly useful. Well, it is for some cryptography things, but we were looking at things that were easier than Shor's algorithm that you could verify fast. The one that's very similar to Shor's algorithm, if you know the structure of Shor's algorithm, it's to find the period of a to the x mod n. This is finding the period of x squared mod n, a so-called Rabin encoding. Not finding the period, but finding that this is a 2-to-1 function, and you're looking for the two colliding inputs, and do they have the same parity or not? Classically, that problem has a 1/2 probability if you just guess. Quantum mechanically, you can do it with 3/4 probability. And so it's it's a sort of a one-way function. And again, I won't get into the details. We verified both of these problems with very small quantum computers with only a dozen or so qubits and 50 or so gates. This is a couple of years ago. I won't talk about this. I would love to, but this is a small circuit that tests something called quantum scrambling, which is thought to occur in black holes. So we made a little 3-qubit black hole here, and all these fancy slides. Lenny Susskind's an expert on wormholes and the conjecture that quantum teleportation through a wormhole is possible. And that connection is, I don't really get it. I'm on thin ice, but there are small circuits that you can test, believe it or not, the thermodynamics of tiny black holes. Really cool connection. And that's just, tip of the iceberg on how you can use these things for science. I want to talk about IonQ, the company I founded with Jungsang Kim about 8 or 9 years ago. And it came about because this venture capitalist named Harry Weller visited my office. He waved a paper in my face. It was an architecture paper on how to scale up quantum computers using optics. Maybe I'll mention that very briefly later. He said, he waved this paper in my face. I didn't know venture capitalists read Physical Review A, but he said, this reads like a business plan. And Jungsang and I sort of put him off. We were very well funded at the university. We didn't want to start a business, but that just got him hungrier. And he eventually got us going. And tragically, right when we got going, he passed away in his sleep. Nobody knows why, but after he passed away, we had to find another champion in Silicon Valley. So I spent a good part of early 2017 in the Palo Alto area. I remember going to Costco to buy clothes for an extended trip that lasted longer than I wanted to. But we did get a few partners to fund the company. I mean, we had a recipe on how to build a scalable quantum computer. It just hadn't been engineered before. And we were buoyed by the fact that it was engineering. We didn't need new physics. Atoms is not new physics. That's old physics. So here's an example of the engineering we've done at IonQ. This is an auto loader. So this is a micrograph of the same ion trap from Sandia. We load ions, if you're wondering how we get them in there, one at a time from this zone, and we shuttle them one at a time to the zone where we do computing. This is a real-time video of loading exactly 24 ions. You can see they're even zigzagged. We straighten them out, and then we refocus the imaging optics. Now we're set for the next several hours. If this chip is cooled to 4 Kelvin, this crystal will stick around as long as the power's on. So this is it's kind of a solid state because they're just sitting there, but it's not. These are perfect individual atoms that we can poke laser beams and run circuits. IonQ has put their systems on the cloud. They were the first company really to put their systems on all 3 clouds. Although, putting a system on a cloud, is a little bit disappointing because it's not the latest and greatest system. But the exercise of doing the engineering so that it runs 24/7 is a big deal. I didn't kind of expect that. The big news at IonQ is several years ago we went public. Everything happened so fast, and I looked up today. It's the market cap of that company is $7 billion. I stepped away from IonQ over a year ago for lots of reasons. That if I could join you for a nightcap or a beer tonight, I would tell you the real story there. But they're too aggressively selling systems. I think you need to sell systems, but I think they should pay maybe a little more attention to research. Now, Russ will talk a little bit about the wonderful things happening at Quantinuum, and they're really approaching scaling in a way that that really is novel to move ions around. He'll tell you. I don't want to steal his thunder. It's a wonderful way of scaling to more than a few dozen qubits by moving atoms around. Another way to scale, I'm almost done here. I know I'm running out of time. And I'm sure Russ won't mind if I cut into his time a little bit. Another way to scale that I think is probably going to be needed for every quantum platform, and that is to make it look like a data center and scaled by using photons. Photons are wonderful quantum particles. They're horrible memories, as we learned from optical computing 30 years ago. But we already have our good qubits. If we can map them to photons in order to route signals around, that's a wonderful modular way to do this to do this scaling. And this, by the way, was what that was the paper that Harry waved, is how to use photons to scale. Sorry for all the motion here. Using photons to scale in a modular way. And if you're worried about this optical switch, there's nothing quantum about it. These are just photons going through fibers. And actually, Jungsang Kim made the biggest photonic switchyard ever about 20 years ago at Bell Labs. This is 1,000 inputs and 1,000 outputs. And one thing I'll say, we don't have a system anywhere near this yet. It is fully connected. You can do a gate between any two qubits in this system without paying a price over distance. That's hugely powerful at scale. As you scale up, things like architecture really, really bad. A very brief comment on error correction. I didn't talk about it because with trapped ions, you don't really need it. The trapped ion native, the idling error is very low, and we don't really need it yet. We need more qubits before we need error correction codes. Now, Robert Calderbank is my colleague at Duke. He also invented quantum error correction with Peter Shor, but he invented a more important form of error correction that we use in our wireless codes. They're called space-time codes. And he's a proponent of not doing error correction for any kind of error. If you have to correct any kind of error, you probably have a bad system. You should learn something about the errors in your system and do something called error mitigation. And this is exactly what's happening in trapped ions to great fanfare. I think the Googles and the Intels and the IBMs, they're doing arbitrary error correction, and they have to think about error correction right at the beginning because their qubits are so horrible. So it's a horrible way to scale. And the overheads they're going to pay are really why they really can't scale. So who's going to build these systems? I sort of mentioned that we need quantum engineers to work on systems they're not used to. Well, universities don't do engineering, and they don't have enough money to build something like that. Industry has the money and the engineering, but they're not yet ready for quantum, it seems. I think they favor solid state too much. I think startups are the great exception here. But I do think in between these, we have national labs and big universities that sort of can maybe bridge both worlds really well. And in terms of the business hype cycle, you might argue in quantum, I mean, the hype's deafening, and we're always at the peak of hype. So we worry about this trough of disillusionment. We do know that there is a slope at the end of the day that's going to be great, but will the investment be patient enough? And I do think using quantum computers for science is a great way to hopefully bridge that trough. It's not commercial activity, unfortunately, but at least we can keep our foot in the door until the floodgates really open. And at Duke, this is a cheap ad, at Duke, this is exactly what we're doing. We're setting up a full stack institute. It's not physics, even though I'm a physicist and an ECE person, it's everything up to computer science and even economics in the business school. People are interested in this. So I know I worn out my welcome on the video screen here. So this is my last slide. It's kind of a funny one. It actually refers to AI from a magazine several years ago, but I think it could also apply to quantum computing. It's somewhere in the middle between hype and hope. So with that, thanks for your attention. And again, apologize for missing you in person.